3,000 miles below your feet, something is shifting that should not be moving at all. Earth's inner core, a solid ball of iron the size of the moon, just slowed down, reversed direction, and started changing shape. Satellites picked up gravity signals that lead straight to the boundary where rock meets molten metal. Tonight we descend through cracking continents, hidden oceans, ghost flows of liquid iron, and a weak spot in our magnetic shield growing faster than anyone predicted. If this kind of journey hooks you, hit subscribe and stay close. Take a deep breath. We are going down. Picture a solid ball of iron the size of the moon hanging in a sea of liquid metal 3,000 miles below your shoes. That ball is Earth's inner core. For most of the past century, scientists believed it spun quietly, faster than the rest of the planet, like a steady gear inside a giant clock. Recent seismic data has shattered that picture. A team led by John Vidal at the University of Southern California spent decades reading the planet's faintest tremors. They focused on a strange tool, repeating earthquakes near the South Sandwich Islands in the deep Atlantic. These are quakes that strike the same spot, again and again, sometimes years apart. Each one fires a sound wave straight through the heart of the planet. By comparing how those waves arrive at distant detectors, scientists can measure motion in the core down to a fraction of a second. What they found surprised even them. By the 1970s, the inner core was spinning a little faster than the planet. It slowed around 2008, and from 2008 to 2023 began moving slightly in reverse relative to the mantle. Imagine driving on a highway, slowly drifting backwards while the road keeps moving forward. That is what the heart of our planet appears to be doing right now. This is a confirmed result, published in the journal Nature. The reversal is small, only fractions of a degree per year, but the implications are huge. The inner core is the engine room. The way it turns helps shape the magnetic shield protecting every living thing from solar radiation. A change in its dance is a change to the rules of our world. The strangest part is that this reversal seems to follow a pattern. By tracking seismic waves from earthquakes that have passed through the Earth's inner core along similar paths since 1964, the authors of the 2023 study found that the spin followed a 70-year cycle, roughly 7 decades of speeding up, then slowing down, then reversing. Our species has only been measuring this for about a single human lifetime, so we are seeing a tiny slice of a very long story. Why does this matter for you? Because the magnetic field that bounces compass needles and guides migrating birds is born from motion deep inside the core. When the gear shifts, the field above shifts too. Pilots, satellites, and power grids all feel the ripples. Some scientists suspect that this 70-year wobble may be linked to slight changes in the length of a day, on the order of milliseconds. Time itself bends just a little as the iron heart flips its rhythm. Vidal himself put it in plain words. He said, "The dance of the inner core might be even more lively than we know so far." And he meant it. The team thought they were going to confirm a steady rotation. Instead, they stumbled into something none of them expected. Then, while studying the slowdown, one signal jumped out of the data, a signal that did not match rotation at all, a signal suggesting the inner core was doing something far stranger than turning the wrong way. It was reshaping itself, and that discovery would crack open every textbook ever written about our planet. What they saw next made the slowdown look almost boring. Vidal's team kept staring at the seismograms, the squiggly lines that record earthquake echoes. They were hunting for proof of the slowdown. Then a few of those squiggles refused to fit the rotation story. The waves were arriving with the wrong shape. Not just early or late, different. He has described the moment in interviews. But as I was analyzing multiple decades worth of seismograms, one dataset of seismic waves curiously stood out from the rest. Vidal said, "Later on, I'd realize I was staring at evidence the inner core is not solid." Read that again. The inner core, the part of the planet textbooks have called solid for nearly 100 years, is doing something that rigid metal should not do. Its surface is moving like soft taffy. Its outer edge is bulging, sliding, deforming. The change is small in human terms, only a few miles, but in geology, a few miles is an earthquake of meaning. Here is the picture. Imagine a giant ball of iron pressed under crushing weight, spinning inside a swirling ocean of liquid metal. The boundary between the solid ball and the liquid ocean is not still. The liquid pushes, drags, and tugs at the iron surface, and the iron flexes back. The team thinks the molten outer core is physically reshaping the inner core's skin, like waves carving a sandy beach over time. This is a confirmed observation published in Nature Geoscience in February of 2025. What we ended up discovering is evidence that the near surface of Earth's inner core undergoes structural change, Vidal said. The deformation is happening right now on human timescales, not over millions of years. That is what makes it so jarring. Why does the surface flex? Scientists are still arguing. One leading theory points to the wild flows of the liquid outer core. Another suggests the inner core's iron is closer to its melting point at the surface than anyone realized, soft enough to slowly creep. Both are theories. The deformation itself is fact. The data came from a remarkable archive. The study utilized seismic waveform data, including 121 repeating earthquakes from 42 locations near Antarctica's South Sandwich Islands that occurred between 1991 and 2024 to give a glimpse of what takes place in the inner core. 33 years of tremors from one of the loneliest stretches of ocean on Earth, all firing through the planet's deepest secret. The ground you are standing on, the floor of every city, every farm, every desert, every ocean, sits on a heart that is changing shape, not metaphorically, literally. While you read this paragraph, 3,000 miles below, iron is bending. This shape change matters because the inner core's surface is where the deepest magnetic action happens. Liquid metal flowing past the bumpy iron surface generates currents. Those currents make the magnetic field. Change the bumps and you change the field above. Change the field and you change how cosmic radiation reaches us, how compasses point, how migratory species navigate. Yet shape change is only one piece of the puzzle. Beneath this shifting surface, a far stranger discovery has emerged about the matter inside. The inner core, scientists now believe, may not even be a normal solid at all. It might be something physics barely has a name for. For 100 years, school books taught a simple story. Earth has a solid inner core and a liquid outer core. Iron in the middle, packed so tight by the weight of the planet that it cannot flow. Strong, frozen, motionless metal. End of story. That story is now broken. In late 2025, an international team announced something that reads like science fiction. The inner core may be a state of matter that does not fit the categories you learned in school. Not solid, not liquid, not gas. Something in between. They call it superionic. Here is the simple version. Inside the core, iron atoms are locked in a tight lattice, like soldiers standing in formation. That part is solid. But mixed in with the iron are lighter elements, including carbon, hydrogen, and oxygen. Under the unimaginable pressure at the center of Earth, those lighter atoms break free of the lattice. They flow through the iron formation like water trickling through a stone wall. The wall stays, the water moves, both at once. To make this discovery, scientists used diamond anvil cells, tiny vices that squeeze samples between two diamonds with pressure higher than anything at the bottom of the deepest ocean. They aimed sound waves through the squeezed iron and recorded how those waves slowed down. By pairing in situ sound velocity measurements with advanced molecular dynamics simulations, the team detected a dramatic loss of shear wave speed and a sharp increase in Poisson's ratio. These results align with the unexpectedly soft seismic characteristics recorded within Earth. Translation: the lab measurements matched the strange softness scientists had been seeing in real seismograms for years. On an atomic level, The data showed carbon atoms moving freely through iron's orderly structure, weakening it without causing the lattice to collapse. Carbon flowing like a hidden river inside what we thought was rock-hard metal. Picture a diamond ring left in the sun. The setting holds, but somehow water is leaking through the gold. That is the closest everyday image. Now scale it up to a metal ball thousands of miles wide, and you start to feel the weirdness. This is presented by the researchers as a strong theory, supported by lab data and matched to seismic observations. It is not yet absolute proof, but it is the best explanation anyone has for puzzles that have haunted geophysics for decades. The implications cascade outward. Atomic diffusion within the inner core represents a previously overlooked energy source for the geodynamo, the team noted. The geodynamo is the engine that makes Earth's magnetic field. If carbon and hydrogen atoms are flowing through the core, they may be feeding extra energy into that engine, affecting the field around your head right now. Stop and let that settle. Every magnetic compass on Earth, every aurora dancing over the poles, every migratory bird that finds its way home, every satellite shielded from solar storms, all of them depend on a process happening inside a state of matter humans only just discovered. What does it mean when our planet's heart turns out to be something physics never had a clean word for? It means the textbooks need rewriting. It means Earth is stranger than the strangest thing we imagined, and the strangeness keeps growing, because the next layer up, between the inner core and the rest of us, is hiding ghosts of ancient worlds. Climb up from the inner core, through the swirling ocean of molten iron, and you reach a place called the core mantle boundary. It sits about 1,800 miles below your feet. Above it, solid rock. Below it, liquid metal. In between, a thin, mysterious layer scientists named D double prime. For decades, it was the strangest neighborhood in the planet, and almost no one could see inside. That changed when a team of seismologists, led by Samantha Hansen at the University of Alabama, set up listening stations across Antarctica. Their goal was to record earthquake waves passing through the deep planet. What they heard back was unexpected. Echoes, pockets where seismic waves slowed down dramatically, as if hitting something denser and stranger than the rest of the boundary. These pockets have a name: ultra-low velocity zones. They sit like dark continents on the rooftop of the core, and the new finding suggests they are not isolated patches. They may form a near-global layer wrapping the core. In simple terms, our planet's heart is wearing a hidden coat. What is that coat made of? The leading theory, presented as a strong hypothesis, is jaw-dropping. It is ancient ocean floor, pieces of seabed that sank into the mantle hundreds of millions of years ago, dragged down by plate tectonics, finally settling at the bottom of the deep planet, like crumbs at the bottom of a bowl. Over the years, some of these submerged plates, once remnants of the ocean floor, settled at the core mantle boundary, forming what scientists have now recognized as an ultra-low velocity zone, ULVZ. Albeit only tens of kilometers thick, this ULVZ layer is significantly denser than the surrounding mantle. Imagine that. The seabeds that dinosaurs once swam over, that ancient ferns and trilobites lived under, did not disappear. Some of them sank, mile after mile, era after era, until they pressed up against the molten heart of the world. Pieces of vanished oceans now keep our magnetic field warm. Hansen described the work as, "Our work is like a high-resolution snapshot of the Earth's inner structure, and boy is it more complex than we ever thought." Her tone of surprise is real. Geophysicists thought the core mantle boundary would be smooth and simple. Instead, they found something closer to a mountain range upside down, with hot, dense ridges and valleys stretching for thousands of miles. This matters for everything above. The presence of this layer could buffer heat flow across the core mantle boundary, which is important because the temperature conditions in this portion of the Earth have been shown to strongly impact the planet's magnetic field, Hansen explained. The ancient seabeds act like a blanket, deciding how much heat escapes from the core into the mantle. That heat flow, in turn, shapes the magnetic field. The seabed coat is a thermostat for the planet. The ghosts of vanished oceans are running the climate of the deep. They guide where mantle plumes rise. They shape where volcanoes erupt at the surface. The dinosaurs walked on a world powered, in part, by even older seas crushed below. This was a slow, silent burial that took hundreds of millions of years. But scientists are starting to suspect that other things are buried down there too. Things much weirder than recycled seafloor. Things that may not be from our planet at all. Above the strange D-double prime layer sits the lower mantle. For decades, geologists drew the mantle as a smooth, soft, slow-flowing rock, like cold caramel, boring, featureless. One giant slab. That picture is also gone. When seismic waves are tracked carefully through the deep planet, two enormous shapes appear. One sits beneath Africa, the other sits beneath the Pacific. Each is thousands of miles wide and hundreds of miles tall. They are denser, hotter, and stranger than the rock around them. Scientists call them large, low shear velocity provinces, but most people just call them the African and the Pacific blobs. Imagine two upside-down mountains, each the size of a continent, planted on the roof of the core. They have been there for a very long time. They are also unlike anything else inside the planet. Seismic waves slow down passing through them. Their edges are sharp, not blurry. Whatever makes them is chemically distinct from the rest of the mantle. Where did they come from? This is where things get genuinely controversial. One leading theory, still debated, is that these blobs are leftover scraps of a crashed planet. Around 4.5 billion years ago, a Mars-sized world named Theia is thought to have slammed into the early Earth. The collision flung debris into orbit, and that debris later became our moon. The mainstream story has always assumed Theia mostly merged into Earth and disappeared. The alternative, proposed in recent years and still being tested, is that pieces of Theia never fully mixed in. Instead, they sank to the bottom of the mantle, settled in two giant blobs, and stayed there. If true, you are walking around on a planet with the corpse of another planet inside it. That is presented as a theory, not a settled fact. The mainstream community still considers it bold, but the blobs are absolutely real, and their composition really does seem alien compared to the surrounding mantle. Whatever they are made of, they have been there for longer than complex life has existed at the surface. These blobs do more than sit. They are where the world's largest mantle plumes rise from. A mantle plume is a hot column of rock that rises slowly through the mantle, like wax rising through a lava lamp. When a plume reaches the surface, it can build a chain of volcanoes. The Hawaiian Islands sit above one such plume. Iceland sits above another. Yellowstone is fed by a third. All trace their roots, scientists believe, down to the edges of the African or the Pacific blob. That means the volcanoes that built whole island chains and the supervolcanoes hiding under national parks are connected to mysterious continents floating on the core. The eruptions you read about in the news have roots reaching almost to the iron heart of the planet. Stop and picture it. Two unknown structures, possibly older than animals, possibly older than the moon, sit beneath your feet. They guide where the planet's hottest rock rises. They influence which coastlines will have earthquakes, which ocean basins will spread, and which volcanoes will roar. Yet even these continent-sized blobs are quiet compared to what happens above them in the swirling outer core itself, because there, fast, violent rivers of liquid metal are flowing, and one of those rivers is doing something nobody can explain. Above the blobs in the inner core, it is a roughly 1,400-mile thick shell of molten iron and nickel, hot enough to vaporize anything from the surface in an instant, dark and heavy and constantly moving. This is where Earth's magnetic field is born. The way the liquid metal flows decides how strong our shield is, how it points, and how quickly it changes. Until recently, scientists could only guess at the flow patterns. The outer core is invisible. No probe will ever reach it. The pressure would crush a submarine to a film. the temperature would melt anything we could send. The only way in is by listening to seismic waves and watching the magnetic field above for clues. Then came Swarm. The European Space Agency launched 3 identical satellites in 2013 to map the magnetic field with unprecedented precision. Year after year, they returned data so clean that scientists could start to reverse engineer what was happening below. And in 2016, that data revealed something nobody had ever seen: a jet stream of liquid iron hidden inside the outer core, a river of molten metal a couple of 100 miles wide, flowing at 3 times the speed of the surrounding fluid, racing westward beneath Alaska and Siberia. Imagine a fast-moving current in the deep ocean, only the current is made of glowing iron, and the ocean is the heart of the planet. This was a confirmed discovery presented in the journal Nature Geoscience, and consistent with multiple follow-up studies. The jet has been speeding up over the years. It is one of the strongest known flows inside the core, and nobody is fully sure why it is there or why it has been accelerating. Why does this matter so much? Because the outer core's flow is the magnetic field. When liquid metal moves through a magnetic environment, it generates electric currents. Those currents make new magnetic fields. The whole system feeds on itself. Geophysicists call it the geodynamo, and it is the reason your compass points north instead of nothing. Speed up a piece of that flow and you change the field above it. Slow it down and you change it differently. Add a hidden jet stream and the patterns at the surface start to make new sense, including some of the strangest features of the modern magnetic field. Picture a swimming pool full of dark, glowing fluid. Now imagine that somewhere inside the pool, a powerful jet hose is firing horizontally, faster than anything around it, dragging swirls and eddies behind. The water close to the jet moves with it. The water near the walls hardly moves at all. That is roughly how the outer core looks now in the eyes of geophysicists, except the pool is the size of Mars and made of molten iron. There is a haunting question lurking under all of this. The jet is changing. The flows around it are changing. Why now? Are we watching a normal cycle that has been going on for billions of years, or are we watching the early stages of something unusual? Honest scientists say it is too early to tell. Our records of the deep field are barely longer than a century, yet the hidden jet is just one of many strange currents now showing up in the data. Some of them are doing something far more disturbing. They are pushing the magnetic field above us into a quiet crisis. Ride the molten currents up to the top of the outer core, and you reach the underside of the mantle. Here, the magnetic field that fills space above the planet has its roots. Most of the field looks neat from above, like the lines of a giant bar magnet. But over one part of the world, the field is doing something wrong. The region is called the South Atlantic anomaly. It is a vast patch of weakened magnetic field that stretches from southern Africa across the South Atlantic to South America. Inside this patch, the shield protecting our planet from cosmic radiation is thinner than it should be. Satellites flying through the anomaly are exposed to noticeably higher doses of radiation. Some have to power down sensitive systems just to get through it safely. The anomaly has been known since the 1800s. What makes today different is that it is growing fast, and the growth was caught in painstaking detail by the Swarm satellites. 11 years of clean magnetic data have now been turned into a sharp public picture. The picture is unsettling. Using 11 years of magnetic field measurements from the European Space Agency's Swarm satellite constellation, scientists have discovered that the weak region in Earth's magnetic field over the South Atlantic, known as the South Atlantic anomaly, has expanded by an area nearly half the size of continental Europe since 2014. Half the size of continental Europe. In just over a decade, that is a confirmed measurement, not a forecast. The shield above one of the busiest oceans on the planet is thinning at a pace geophysicists called surprising even to themselves. The minimum strength inside the anomaly has dropped too. The minimum intensity has fallen from about 22,430 nanotesla in 2014 to 22,094. This is a substantial reduction for a field that normally changes very slowly on decadal scales. A field that should creep along on geological timetables has been losing strength on the timetable of a single career. What does that mean for daily life? Almost nothing on the surface. People in Brazil and Argentina do not feel weaker magnetism in their bones. Compasses still work. The atmosphere still soaks up most cosmic rays. The story is different in low Earth orbit satellite infrastructure, Finlay said. These satellites experience higher rates of charged particles when they pass through the weak field region, which can cause problems for the electronics. Astronauts feel it too. People aboard the International Space Station report seeing strange flashes inside their closed eyes when passing over the anomaly. Those flashes are cosmic ray particles slamming into the back of the eyeball. The shield is too thin to stop them all. Now imagine the same problem multiplied across thousands of new low-orbit satellites racing to fill the sky, and the future starts to feel busier. The lead author of the study put the mystery in plain words. There's something special happening in this region that is causing the field to weaken in a more intense way. Special. That is the polite scientific term for we don't fully understand it yet. Yet within this giant weak spot, satellites just spotted something stranger. The patch is splitting in two. Earlier this decade, NASA scientists watching the South Atlantic anomaly noticed that the weak patch was no longer one smooth dent in the field. A second, distinct minimum was forming inside it. The single anomaly was beginning to split into two. By 2020, the split was clear. By 2025, the picture had grown more dramatic. Two separate weak cells now sit inside what used to be one, like a pothole cracking open into a pair of pits. Why would a magnetic anomaly split? The honest answer is that we are still piecing it together, but the leading theory points back to the core. Below the South Atlantic, the liquid metal at the top of the outer core seems to be doing something unusual. There are patches where the magnetic field, instead of pointing up out of the core like normal, points back down into it. These are called reverse flux patches. They are like little magnetic dimples on the rooftop of the molten ocean. When those dimples grow, the field directly above them weakens. When two dimples migrate near each other, the weak zones on the surface start to merge or split. Normally we'd expect to see magnetic field lines coming out of the core in the southern hemisphere, but beneath the South Atlantic anomaly, we see unexpected areas where the magnetic field, instead of coming out of the core, goes back into the core. Thanks to the swarm data, we can see one of these areas moving westward over Africa, which contributes to the weakening of the South Atlantic anomaly in this region. That is a vivid image. Picture the field lines like glowing threads sprouting from the ground. In one neighborhood, the threads are not sprouting, they are diving back in, and the neighborhood itself is sliding sideways across the deep planet. The recent results show that this internal motion is not slow background noise. The new swarm analysis shows that one of these reversed flux features beneath southern Africa has moved westward, while another, beneath the central South Atlantic, has drifted eastward, bringing the two into a closer and more complex interaction. This internal flux motion produces the surface expression mapped as the anomaly. The study's maps show that the weak field region has not just expanded, but also reshaped itself, with the most dramatic deepening occurring where these core flows converge. Two hidden currents in the deep core, drifting in opposite directions, are colliding underneath the Atlantic Ocean. Where they meet, the shield gets thinnest. Where they pull apart, the dimples spread. The split at the surface is the bruise. NASA geophysicist Weijia Quang offered a clean way to think about it. The observed SAA can be also interpreted as a consequence of weakening dominance of the dipole field in the region. She added, more specifically, a localized field with reversed polarity grows strongly in the SAA region, thus making the field intensity very weak, weaker than that of the surrounding regions. A small reverse magnet is growing inside the big normal one. That smaller magnet is fighting the field, eating into it from below. Should we worry about this? Geophysicists are careful here. The split is real, the weakening is real, but no current data shows our planet is about to flip its magnetic poles. The anomaly is a slow, deep wobble, not a switch. Even so, the satellites are now picking up something even more startling on the other side of the world. The shield is changing in places. While the south thinned, scientists assumed the north was steady. The northern half of Earth's magnetic field has two strong centers, one beneath Canada and one beneath Siberia. For most of recorded history, these centers have been the anchors of the field, the reliable parts. They are why a compass works at all in places like New York, London, or Tokyo. The Swarm satellites just found that those anchors are slipping. However, since Swarm has been in orbit, the magnetic field over Siberia has strengthened, while it has weakened over Canada. The Canadian strong field region has shrunk by 0.65% of Earth's surface area, which is almost the size of India, while the Siberian region has grown by 0.42% of Earth's surface area, which is comparable to the size of Greenland. A region the size of India has lost magnetic strength under Canada. A region the size of Greenland has gained it under Siberia. In just over a decade, that is, the magnetic version of moving a mountain. The lead author called this unexpected. It is related to the circulation patterns of the liquid metal in the core, but we are not certain of the exact cause, he said. Liquid metal currents at the rooftop of the core are dragging the strong patches around like clouds in a slow wind. We can map the clouds. We cannot yet predict where they will be next century. Picture a giant invisible stage spotlight. For decades, the spotlight pointed straight down at northern Canada, lighting up the Arctic. Now it is dimming on the Canadian side and brightening on the Russian side. The spotlight is tilting, and every navigation system on Earth has to keep up. This is more than a curiosity. The magnetic North Pole has been racing across the Arctic for decades. In the 1900s, it crept along at a few miles a year. By the early 2000s, it was sprinting at over 30 miles a year, almost in a straight line from northern Canada towards Siberia. The shift in the deep core flows is widely believed to be the cause. The Siberian patch grew strong enough to pull the pole toward itself, like a child winning a game of tug-of-war. Aviation cares deeply about this. Airlines, militaries, and shipping fleets rely on a model called the World Magnetic Model to keep their compasses honest. When the pole moves faster than expected, the model has to be updated out of schedule. That happened in 2019, when an emergency update was issued ahead of time because the pole had drifted further than predicted. It has happened again since. The compass is not lying. It is just chasing a target that will not sit still. For most of human history, the field has been treated as background, a constant, like gravity. The new data forces a different view. The field is alive. It bulges. It thins. It walks across the planet at a jogger's pace, and the things that decide how it moves are happening inside something we cannot ever see directly. Yet of all the strange behaviors of the field, none has shocked scientists more than what comes next. Because hidden inside the core, an entirely new kind of wave was just discovered, a wave nobody knew was possible. To understand the next discovery, picture the outer core as a huge pot of glowing soup. The soup is liquid iron. The pot is rocky mantle. As the soup cools at the top and heats from below, it slowly churns, and it carries the magnetic field along with it. For a long time, scientists believed the only waves rippling through this soup were big, slow ones, waves that took thousands of years to cross the core. Then, about 3 years ago, an international team announced something startling. They had detected a brand new kind of wave inside Earth's core, a faster, sharper kind, completing a full cycle every 7 years. They called them magnetocoriolis waves. They behave like vibrations on a giant invisible drum, but the drum is made of molten metal, and the drumstick is the Earth's spin. Here is the simple version. Liquid metal in the core is constantly stirred by the planet's rotation, by buoyancy, and by the magnetic field itself. When all three forces tug on a flowing parcel of iron, that parcel wobbles, the wobble travels, it bends, it speeds along the surface of the outer core, producing a pattern that the satellites above can finally see. This is presented as a confirmed observation, found by combining decades of magnetic measurements from satellite missions and ground stations. The 7-year rhythm jumped out of the data after careful processing. It matches predictions made years earlier on paper, before anyone had a chance to check. Why is this such a big deal? Because new waves mean new windows into the deep. Each wave is a kind of message bottle from the core. By studying their shape, scientists can deduce how strong the deep magnetic field really is, how fast the iron is moving, and how the inner and outer cores interact. That underground field deep inside the core could be 10 times stronger than the field at the surface. We had no direct way to test that before. Now we have a tool. Picture a doctor pressing a stethoscope to a patient's chest. For decades, geophysicists could only listen for the loud, slow heartbeat of the deep field. Now they have a faster, finer signal, a pulse on top of the pulse. They can hear the patient breathe. These waves also seem to track changes in the length of a day. Earth's rotation speeds up and slows down by tiny amounts, on the order of a millisecond, in roughly 7-year cycles. That cycle lines up uncannily with the new waves. It is a strong hint that the deep core, the magnetic field, and the spin of the planet are all coupled in a single dance. When one shifts, the others ripple. Stop and feel the strangeness here. Your day is, in a sense, slightly steered by waves of liquid iron miles below your feet. The very length of your Tuesday is connected to vibrations in a metal you will never see. What ties all of this together is the realization that the core is not an empty engine quietly humming. It is full of motion humans have only just learned to detect. And the more we look, the more we find, including the unsettling possibility that the core is leaking something most of us think can never escape from such a place. Gold. Most of Earth's gold is locked deep inside the core. When the planet was young and partly molten, heavy metals sank toward the center, while lighter rock floated up to form the mantle and crust. Estimates suggest enough gold may sit inside the core to coat the entire surface of the planet in a thick layer. That treasure has always been considered unreachable, out of sight, out of mind. That assumption was challenged in 2025. A team of scientists analyzing volcanic rocks from Hawaii found something they did not expect. Inside the rocks were chemical signatures that should not exist if all the deep gold had stayed put. Specifically, ratios of certain isotopes of metals like ruthenium pointed to material that came from the very edge of the core, not just the mantle. In simple words, the volcanic rocks of Hawaii are wearing a faint perfume from the deep core, and one of the molecules in that perfume is gold. Tiny amounts, atom scale, but measurable, and present where they should not be. How can metal escape a place wrapped in thousands of miles of solid rock? The leading theory points to the mantle plumes mentioned earlier, the slow, hot columns of rock that rise from near the core mantle boundary. As these plumes rise over hundreds of millions of years, they may pick up traces of material from the rooftop of the core. When the plumes finally erupt at the surface, those traces ride along. Hawaii sits above one of the most powerful plumes on the planet. So does Iceland. So do other ocean island chains. Each of them, the new study suggests, may be quietly bringing fragments of the core's edge to the air. The result is a slow, almost imperceptible bleeding of treasure from the planet's heart. Stop and let the picture form. For most of human history, civilizations have hunted gold in rivers, in deserts, in mountain veins. People have killed for it, traveled for it, dreamed of it. None of them knew that the gold they were finding may have spent part of its journey inches above the molten heart of the world before being thrown skyward by a volcano. This is presented as a strong hypothesis, supported by isotope evidence, but not yet a fully closed case. The leakage rate is small enough that there is no risk of the core running out of gold anytime soon. We are talking about fractions of grams across vast spans of time. The point is not the quantity. The point is the principle. The deep planet was supposed to be sealed. It is not. Material moves between the core and the mantle. It moves between the mantle and the surface. Slowly, painfully, on geologic timescales, even something as dense as gold can travel from the bottom to the top of the world. This changes how scientists think about Earth as a system. The crust we live on is connected to the core by tiny chemical threads we are only just learning to follow. Volcanoes are not only fire, they are messengers. Each ancient eruption may be a postcard from a place no human will ever see. Yet gold is a small messenger. There is a far stranger guest hidden in the same rocks. A guest left over from the very birth of our solar system. Lava flows from places like Iceland and Hawaii do not only carry traces of metal. When scientists carefully trap the gas bubbles inside fresh lava, they find something stunning. Among the ordinary gases is helium-3, a rare isotope that almost no process on the surface of Earth can create. The amount of helium-3 in mantle plume eruptions is far higher than what comes out of normal volcanic regions. That is a confirmed observation supported by decades of geochemistry work. Why does it matter? Because helium-3 is widely interpreted as a fingerprint of the early solar system. Stars and the primordial nebula made it in abundance. Most of it on Earth should have escaped to space billions of years ago. Yet some is still leaking out, fresh, from deep below. The leading interpretation is that this helium has been hiding inside Earth's core, or at the boundary just above it, since the planet first formed. The plumes carry that ancient gas to the surface like a slow elevator. Rare primordial gas may be leaking out of Earth's core, is how researchers have framed the headline. Stop and try to feel the timescale. The helium that bubbles out of fresh lava in Iceland may have spent 4.5 billion years trapped near the core. It has waited there since before life evolved, before the moon settled into its orbit, before the surface of Earth even cooled. Then, in your lifetime, it finally hit the air. Geologists who sniff that helium are sampling the literal breath of the newborn Earth. This insight reshapes another mystery. Where did Earth's water come from? For decades, the textbook answer was comets and asteroids, slamming into our planet long after it formed, and dumping ice on the surface. New research is pushing a different story. Water, or at least its building blocks, may have been baked into the planet from the very beginning, especially in the core. A study highlighted in early 2026 laid out the case in striking numbers. Calculations revealed that this ratio represents at least 9 and at most 45 ocean volumes of hydrogen. Translated, the iron at the heart of the planet appears to hold enough hydrogen locked into its structure to make tens of present-day oceans worth of water. Lead author Dongyang Huang stated that these results suggest Earth may have acquired most of its water during its formation. This discovery offers a strong alternative to the prevailing scientific view that water was later transported to Earth by comet impacts. According to Huang, most of the water in the first million years of Earth's history may have been stored in the core. That is still being debated. Comet and asteroid impacts almost certainly added water too. The new claim is that they were a topping, not the main course. The bulk of our planet's water budget may have been native, born with the core. If that is right, the iron heart of Earth is not just a magnetic engine. It is a hidden reservoir of hydrogen, helium, carbon, and possibly other elements. A primordial vault that has been quietly leaking its contents to the surface for billions of years. The next leak found in Earth's interior would shock geophysicists even more, because it suggests the boundary between the deep core and the rest of us may be cracking in a way nobody expected. The core-mantle boundary is sometimes drawn as a smooth ball. Earlier chapters already showed that this is wrong. The The boundary has mountains of recycled seabed sitting on it, continent-sized blobs above it, and patches of reversed magnetism just under it. New work suggests it has something else too: cracks, or at least zones where material seems to be slipping through it in odd ways. A recent paper using gravity recovery and climate experiment satellites, the GRACE satellites, found a haunting signal. These satellites were originally launched to track water on the surface. They measure the planet's gravity by how their distance from each other changes as they orbit. A heavier mountain pulls the lead satellite down a tiny bit. A drying lake lets it rise. Their precision is so high that they can sense changes 1,000 miles below. Between 2006 and 2008, a peculiar gravitational signal emerged in the data. The lead satellite slightly pulled away from its trailing partner in a manner that could not be explained by surface water or ice movement. Instead, scientists traced the signal to the boundary between Earth's solid mantle and its partially liquid core, nearly 2,900 kilometers beneath the surface. 1,800 miles below us, mass was redistributing in a way that could be detected from orbit. Whatever moved was big enough, dense enough, and fast enough to nudge satellites circling the planet hundreds of miles up. The leading interpretation is that this signal traces movements of dense material right at the core mantle boundary: liquid iron sloshing against the mantle ceiling, patches of dense rock falling into the upper outer core, or pieces of those ultra-dense ULVZ structures shifting position. The discovery did two things at once. It confirmed that the core mantle boundary is alive and changing on human timescales, not just geological ones, and it proved that satellites in orbit can hear the heartbeat of the deep planet, not only by magnetism but also by gravity. We now have two stethoscopes pressed to Earth's chest. Picture a giant balcony deep underground. The floor of the balcony is the top of the molten core. The ceiling is the bottom of the rocky mantle. For most of geological history, scientists pictured this balcony as still. The new gravity data shows that the railings are creaking. Heavy objects on that balcony are shifting from one side to the other, slowly, but enough to be felt all the way at the surface. What does this mean for life on top? In direct, daily ways, almost nothing. Nobody felt the gravity blip in 2006. The signal was buried inside data and required satellites to find. In bigger ways, it means our model of the deep Earth is too simple. The boundary is not a hard line. It is a busy zone where matter exchanges between two completely different worlds, the rock above and the metal below. This has consequences for everything that depends on the deep planet: heat flow into the mantle, the strength of the magnetic field, the rate of mantle plumes, even the long, slow drift of continents at the surface. The cracks and shifts at the bottom shape the architecture at the top. That architecture is also moving, and the most striking surface expression of all this churn happens when one piece of crust dives back down toward the core, in a place called a subduction zone. A subduction zone is a place where one tectonic plate slides under another and sinks into the mantle. The Pacific Ring of Fire is built almost entirely from these zones. Japan, Indonesia, Chile, the Pacific Northwest, all of them sit above slabs of crust, diving down at angles, sometimes steep, sometimes gentle. These slabs do not stop near the surface. They keep sinking, slowly, for hundreds of millions of years, until they reach the bottom of the mantle and pile up against the ultra-low velocity zones. In other words, every great earthquake along the Pacific Rim is a single frame of a long movie. The movie ends with that piece of crust pressed against the rooftop of the core. The movie is so slow that no human will ever watch it from start to finish. But scientists can map every frame. Recently, seismic imaging has reached a new level of clarity. Researchers can now see the cold, dense slabs draped over the core mantle boundary like a cloth thrown across a lampshade. Some of those slabs trace back to oceans that closed before the dinosaurs walked. Their original water has long since been crushed out. Their original salt has long since been swept up into volcanic arcs. What is left is bare, cold rock planted at the deepest place rock can go. This connects everything. The recycled seabeds at the core mantle boundary discussed earlier were, once upon a time, slabs in subduction zones. Today's subducting plates will become tomorrow's ULVZ structures. The core mantle boundary is slowly being repainted generation by generation by the slow plunge of the surface into the deep. There is a darker twist. As slabs sink, they release water trapped inside their minerals. That water rises into the mantle and fuels volcanoes. It also changes the strength of the rock around it. Some of the most violent eruptions on the planet, including the kind that buried Pompeii and the kind that explodes from places like Mount St. Helens, are powered by water dragged down with the plates and then squeezed back up. The connection to the core is subtle but real. Heat rising from the core warms the mantle. The warmer mantle convects more vigorously. Vigorous convection pulls plates apart and pushes them under one another. Those plates dive, drag water down, fuel volcanoes, and eventually settle near the core. Then their cold weight on the core's roof tweaks how heat escapes from the iron heart, which feeds back into magnetic field changes far above. Picture a giant water wheel running at the speed of stone. The crust feeds the wheel from above, the core feeds it from below. Every earthquake felt by a city on the Pacific Rim is one tiny click of that wheel turning. Every volcano along the Pacific coastline is a puff of steam coming off it. Every shift in the magnetic field is a wobble in the gear ratios. What we are starting to see with all the new data is that this wheel is not as steady as it once seemed. Plates have been moving in unexpected directions. New slabs are being detected in the deep mantle, including some beneath places that were never thought to host much subduction. The architecture is more complex than the textbooks said, and nowhere is that complexity more visible than in a single, lonely place at the bottom of the world, a region called the South Sandwich Slab. The South Sandwich Islands are a tiny arc of volcanic peaks in the cold southern Atlantic, halfway between South America and Antarctica. Few people live near them, even fewer visit. From the air, they look forgettable, a string of black dots in a grey ocean. From below, they are anything but. These islands sit above one of the most important small subduction zones on the planet. A piece of seabed is diving into the mantle right beneath them. Earthquakes happen there constantly, and most of those earthquakes never make news. Yet they have changed the way we see the deep earth more than almost any other source. That is because earthquakes from the South Sandwich region produce seismic waves that travel almost straight through Earth's inner core, on their way to detectors in the northern hemisphere. The geometry is rare. Most earthquakes do not line up so cleanly with the deep core in a distant network of seismometers. The South Sandwich quakes do. This is why so much of the recent inner core research uses South Sandwich data. The study utilized seismic waveform data, including 121 repeating earthquakes from 42 locations near Antarctica's South Sandwich Islands that occurred between 1991 and 2024 to give a glimpse of what takes place in the inner core. Without these obscure quakes, the slowdown, the reversal, and the surface deformation of the inner core would all still be guesses. A volcanic chain so isolated that most maps of the world barely label it has been quietly broadcasting the deepest secrets of the planet. Each earthquake under those islands is a flash of light through the planet, lighting up the heart for an instant. Stitched together over 33 years, those flashes built the strongest picture we have of the inner core's recent strange behavior. There is something almost poetic about the geography, a small slab of ocean floor diving down at one end of the planet. Echoes from the iron heart at the other end. A handful of seismometers on cold, snowy ground, recording squiggles that almost no one will ever look at. Out of all that, the entire world's understanding of the deep earth has shifted. The South Sandwich Slab is also a window into the future of the core mantle boundary. As that slab sinks deeper over the coming 100 million years, it will eventually settle near the underside of the mantle. it may add to the patches of dense, slow material there. The story coming together suggests that subduction zones are the slow-motion construction crews of the deep, building the structures that will shape the magnetic field of distant tomorrows. Stop and feel that strange double image. A modern fishing boat drifting near these icy islands sits above a region where the surface is being dragged down, and at the same time directly opposite a region where the iron heart is twisting, slowing, and changing shape. Two ends of the planet's deepest plumbing meet here, in a place almost no human visits. The story of Earth's inner machinery does not stop at the slab. Once the slab is buried, water and hidden minerals start to ride along with it, even deep into the mantle. And that has led to perhaps the most surreal discovery of all. There is a hidden ocean inside Earth's rock, far from the surface seas we know. Standing at any beach, the oceans seem like the biggest body of water imaginable. Take all the seas and pour them into one pile, and you get an enormous volume. Now hold that picture in your mind and consider this. Inside Earth's mantle, locked into the structure of a mineral most people have never heard of, scientists believe there could be a quantity of water at least as large. The mineral is called ringwoodite. It is a deep blue glassy form of olivine that only forms under extreme pressures hundreds of miles below the surface. In 2014, researchers studying a tiny piece of ringwoodite trapped inside a diamond from Brazil discovered something remarkable. The mineral contained roughly 1.5% water by weight, not as flowing liquid, but as hydroxyl groups bound into its crystal structure. That sounds tiny until you do the math. The part of the planet we deal with most of the time, assuming we don't have a large mole person readership, is the crust, the uppermost layer that's about 30 miles, 48 kilometers, thick at its biggest. Beneath that is the mantle, which is itself made of 3 different sublayers: the upper mantle, the transition zone, and the lower mantle. Together, they're about 1,800 miles, 2,900 kilometers, thick, and they make up about 84% of the planet's volume. Down beneath the mantle is the core, but it's in the mantle that you'll find our secret 6th ocean. Multiply a small percentage by the unimaginable volume of the mantle's transition zone, and you get a hidden water reservoir potentially larger than every surface ocean combined. Some estimates suggest the equivalent of 3 oceans is locked into the deep rock. That is a strong scientific theory, supported by both the diamond evidence and seismic studies showing low-velocity zones consistent with hydrated minerals. This is not water like a beach. There is no shoreline, no fish, no waves. The water exists chained to mineral structures. A geologist could not scoop a cup of it, yet it behaves like a planetary buffer, absorbing and releasing water as plates dive into the mantle and as plumes rise out of it. The deep mantle is a sponge. The surface oceans we know may simply be droplets resting on top of a soaked, stony body. Why does any of this matter? Because the water in the mantle changes how rock flows. Water makes rock weaker, easier to bend, easier to convect. That weakness controls how fast the deep mantle stirs, which controls how heat moves out of the core, which feeds back into the magnetic field. Once again, every layer is talking to every other layer. The mantle ocean also reshapes the question of habitability. Other rocky planets in the universe may have similar water reservoirs locked in their interiors, even if their surfaces appear bone dry. Mars and Venus, for example, may carry hidden water budgets that surface telescopes cannot see. Earth's discovery is a hint that worlds without oceans may not be worlds without water. Stop and try to grasp it. Beneath your feet, hundreds of miles down, sits a body of bound water bigger than every river, lake, sea, and ocean combined, held inside blue crystal under crushing pressure. It has been there for billions of years. It will be there for billions more. The story of every drop you drink is older than rain. There is one final twist deeper still, because the very same chemistry suggests that even more water lies even further down, inside the core itself. a buried ocean we may never see. If the mantle is a stony sponge soaked with bound water, the core may be even wetter, in a different way. Hydrogen, the essential building block of water, bonds eagerly with iron under high pressure. Inside the inner core, conditions are perfect for that bonding to happen on a planetary scale. Scientists working with diamond anvils and computer simulations have been arguing for years that the core may contain an enormous hidden hydrogen budget. The latest results push that number higher than anyone expected. The recent paper led by Dongyang Huang summed it up. Calculations revealed that this ratio represents at least 9 and at most 45 ocean volumes of hydrogen. 9 to 45 oceans worth of hydrogen locked inside the metal heart of our world. Research data shows that the core is followed by the mantle and crust in terms of water abundance, and that the surface is actually the planet's driest layer. The surface, the place where every river runs and every ocean rolls, is the driest layer of Earth. This is presented as a strong, fresh hypothesis, not yet a closed case. Direct sampling of the core is impossible. The argument rests on lab experiments, theoretical chemistry, and matches with seismic data. But the math is strikingly consistent. Iron under core conditions wants to grab hydrogen. The amounts grabbed are huge, and the implications change planetary science. If most of Earth's hydrogen has been parked inside the core since formation, then most of our water was never an alien delivery. It was native. It was there in the dust cloud that birthed the planet. Some of it bonded with iron and sank with the metal. The rest stayed up high to form the oceans, the atmosphere, and eventually the rivers that grew civilizations. The deeper point is even bigger. The inner core may not be an inert lump. It may be a slow leaker, releasing tiny amounts of hydrogen to the outer core over geological time. That hydrogen affects how the liquid iron flows, which affects the magnetic field, which affects life. Atomic diffusion within the inner core represents a previously overlooked energy source for the geodynamo, the team behind the superionic discovery noted. A hidden ocean of hydrogen in the heart of the planet may, in part, be the reason the magnetic shield exists at all. Picture the planet as a layered cake, the icing as the crust, where humans live. Beneath that is the spongy mantle, with its bound oceans of water. Beneath that, the swirling outer core threaded with jets and reverse flux patches. At the very center, a glowing iron pearl, soft at the surface, possibly superionic inside, holding tens of oceans worth of hydrogen in its lattice. Every layer is a world of its own, and they are all connected by slow, invisible flows. Stop and feel the inversion. The surface, where we live and breathe, is the thinnest, driest, most fragile layer. Everything below is heavier, hotter, wetter. Civilization is a film clinging to the top of an ocean of stone, sitting on an ocean of metal, holding a hidden sea of hydrogen at its center. Yet the journey down is far from over, because once you accept that the core is a vault of strange matter and ancient water, a new question follows. What signals have been coming up from this vault recently that scientists never saw before? In the past few years, deep Earth scientists have been talking quietly about what they call unexpected signals. These are not single dramatic events, they are patterns, subtle pulses in the magnetic field, in the gravity field, and in the rate of changes at the core mantle boundary that arrive faster than older models predicted. The deep planet seems to be doing more often than textbooks expected. One example came from the swarm satellites. As they tracked the magnetic field year by year, they noticed sudden jolts. Geophysicists call them geomagnetic jerks. A jerk is a quick change in the rate at which the field is shifting. Imagine driving a car at a steady speed, then briefly pressing the gas pedal, then easing off. The speed changes, but more importantly, the way the speed is changing has changed. That second derivative is what a jerk looks like in the field. Older records suggested jerks happened roughly once a decade. Recent observations show clusters of jerks arriving more frequently, and in places that earlier models did not predict. The leading theory is that these jerks come from sharp wave-like events deep in the outer core, possibly the same magneto-Coriolis waves discussed earlier, breaking against the rooftop of the molten ocean. Why does this matter for ordinary people? Because every aviation chart, ship compass and pipeline survey relies on a stable model of the field. When jerks arrive unexpectedly, the world magnetic model has to be patched. That happened earlier this decade, when an emergency update was issued ahead of its normal 5-year cycle. The field had moved more than expected, and the planes and ships needed correction. There is also a mystery in the gravity data. The GRACE satellites, mentioned in Chapter 13, do not only see one signal from the deep core. As more data has accumulated, more anomalies have shown up. Brief, faint pulses of mass redistribution far below the surface, lasting months or years before fading. Each one points to a slightly different region of the core mantle boundary. Each one is a hint that material down there is more mobile than we thought. Picture a giant invisible drum being tapped from the inside. Each tap is too soft to feel. Each tap is too brief to hear. But sensitive instruments above the drum, watching the skin shimmer, can count them. The taps are speeding up, or at least we are catching them more often. Honest scientists are careful here. Some of the apparent acceleration may be a result of better instruments, not a busier planet. We did not have swarm-level magnetic data before 2013. We did not have GRACE-level gravity data before 2002. A wider window into the core could simply mean we are seeing pulses that were always there, finally clear enough to count. Even so, the picture is shifting. The deep planet is being treated less and less as a slow background and more as a dynamic system that changes on years and decades. The magnetic field, the gravity field, the day length and the inner core's rotation all wobble together in ways that suggest a tightly coupled engine. That coupling is what scares some researchers, because if the engine is tied together, then a sudden change in one part might ripple through the others faster than we can adjust. A skeptic might call that paranoid. A geophysicist would simply call it humility. The next pulse is one of the most jarring of all. It changed how scientists think about the very rotation of Earth itself. For most of recorded history, a day on Earth has been getting longer, very slowly. The Moon is gradually drifting away, and as it does, it tugs on Earth's rotation and slows it down. Each century steals about 1.5 milliseconds from a day. Atomic clocks pick up the difference. Leap seconds are added to keep our human time aligned with the planet. Then, starting around 2020, something flipped. Earth started spinning faster. By 2022, the planet recorded its shortest day on record. By the middle of this decade, several more shortest day records had been set. Time itself, measured by the planet's spin, suddenly reversed its long, slow trend. This is a confirmed observation, captured by atomic clocks and the International Earth Rotation and Reference Systems Service. The change is tiny, fractions of a millisecond, but in the world of precision timekeeping, it is enormous. It even raised the possibility of a negative leap second, where humans would subtract a second from official time rather than add one. That has never happened before. What is causing it? There is no single answer. Multiple culprits are likely working together. One leading suspect is, of course, the deep core. As the inner core slowed and reversed, the outer mantle and crust may have responded by speeding up slightly, in the way a figure skater pulling her arms in spins faster. Another suspect is the redistribution of mass at the surface. When ice sheets melt and water moves toward the equator, the planet's spin slows. When water moves toward the poles, or when the deep mantle redistributes mass differently, the spin can quicken. Climate change is pulling in one direction. Core dynamics may be pulling harder in the other. Imagine a spinning top. If you press a finger gently on its widest part, it slows. If you slide a tiny weight closer to its axis, it speeds up. Earth is doing both at once, and the net result is faster days right now. Why should this matter to anyone outside a physics lab? Because computer networks, GPS satellites, financial trading systems, and global positioning rely on time being treated as steady. When the planet refuses to stay on a predictable rotation schedule, those systems need updates. Adding a leap second already creates havoc in some software. Subtracting one would be unprecedented and risky. There is also a deeper reason. The change in day length is one of the strongest hints that the inside of Earth is talking to the outside in real time. The 7-year wave in the magnetic field lines up with a roughly 7-year wobble in day length. The slowdown of the inner core lines up with a shift in day length. The deep core, the magnetic field, and the planet's spin are all dancing together in a single rhythm we have only just learned to hear. Stop and feel that. Your morning, the precise moment the sun rises tomorrow, is being tweaked by molten iron movements thousands of miles below the ocean. Not by a noticeable amount, but by a measurable one. The planet's clock is wired to a hidden engine. What kind of engine could pull that off? An engine fueled by an extreme heat source. A heat source that even after 4.5 billion years refuses to cool down. Which raises a question that has bothered scientists for over a century. Why is Earth still hot inside? Earth was born in a furious blaze. Pieces of rock and metal slammed together, releasing heat. Heavy elements sank to the center, creating more heat. Radioactive elements scattered their own slow burn. By the time the planet had its rough modern shape, the inside was glowing hot. Common sense says 4.5 billion years should be enough to cool a ball of rock and metal completely. Yet, the inside of Earth is still glowing. The temperature at the core mantle boundary is around 4,000 degrees Celsius. The center of the inner core is around 6,000 degrees, comparable to the surface of the Sun. After all this time, the planet has cooled less than many models suggest it should have. What keeps it warm? 3 sources are doing the heavy lifting. The first is the original heat from formation, called primordial heat. The second is energy released as the inner core slowly grows by freezing iron from the outer core. The third is radioactive decay of elements like uranium, thorium, and potassium, all of which release heat as they break down. Recent research has shifted estimates of how much each source contributes. New particle detectors deep underground can measure tiny ghostly particles called geoneutrinos, which are released by radioactive decay inside the planet. By counting geoneutrinos, scientists can directly estimate how much heat comes from radioactivity. The latest estimates suggest about half of Earth's heat output comes from this source. The rest is left over from formation and from the slow growth of the inner core. Picture a giant battery buried inside the planet. Half of it is radioactive fuel cells, slowly burning down. The other half is a thermal storage tank, still releasing warmth from the day it was built. Together, they leak about 46 trillion watts of power into space, every second, year after year. 46 trillion watts is a strange number to picture. It is far more than all human energy use combined. It is the steady output of a star-sized engine operating quietly under your kitchen floor. And almost all of it comes from a place we will never visit. Why should you care about heat in the deep planet? Because every dynamic process discussed in earlier chapters is powered by it. The convection of the mantle is driven by heat trying to escape. The plate tectonics that build mountains and trigger earthquakes are driven by mantle convection. The dynamo that creates the magnetic field is driven by the heat difference between the inner core and the rest of the planet. No internal heat, no plates, no field, no us. There is also a long, slow story to consider. Mars used to have a magnetic field, so probably did the Moon at one point. They lost their fields when their interiors cooled too far. Without the shield, solar wind stripped away their atmospheres, oceans, if they ever existed at the surface, evaporated into space. Both worlds went from possibly habitable to harsh. They aged faster than Earth because they were smaller and could not hold their heat. Earth is bigger, it cools more slowly, it has held on to its dynamo, but it is not immune. Eventually, billions of years from now, the inside will cool enough that the dynamo will stutter and fail. The shield will collapse. The story of life on the surface, in its current form, will end. That is far in the future, yet within our lifetimes, the engine has already begun making sounds that puzzle the scientists listening to it. For most of the past century, geophysics talked about two cores, the solid inner core and the liquid outer core. Two simple layers, one inside the other. As the data has improved, that picture has shattered. There is now strong evidence for a third structure, a so-called innermost inner core, a small distinct ball nested inside the inner core, like a Russian doll. This finding, announced a few years ago and refined since, comes from earthquake waves that pass through the very center of the planet. When researchers stack thousands of such waves and look for tiny differences in their arrival times, they see a pattern. Waves crossing the deepest few hundred miles of Earth seem to behave differently than waves crossing the rest of the inner core. The simplest explanation is that the very middle is structurally distinct. The innermost inner core is small, only about a third of the size of the inner core itself. Its iron crystals appear to be aligned in a different direction than those of the surrounding inner core. Imagine two layers of a wood log, where the grain runs east-west in the outer layer and runs north-south in the inner layer. The boundary between them shows up clearly in the way sound waves bounce. This is presented as a strong observation, broadly accepted by the seismological community, even though the exact thickness, shape, and origin are still debated. The leading theory is that the innermost inner core is an even older piece of the planet, frozen in earlier and locked in by later layers. As the inner core grew over billions of years, the conditions of crystallization changed. The innermost ball formed first in different conditions, and the outer shells of the inner core grew around it later. Picture a frozen pond growing in winter. The first ice forms in one direction, with crystals pointing one way. As more freezing occurs, conditions shift, and the new ice grows with crystals pointing differently. The boundaries between layers stay visible long after the freezing stops. Inside Earth, the same process plays out at planetary scale on a timescale of 1 billion years per layer. Why does that matter? Because each layer is a fossil of a moment. The innermost inner core may carry chemical and structural memories of the earliest dynamo, when the planet was still young and bombarded by impact. By studying it carefully, geophysicists can reach back to a chapter of Earth history hidden by all the violence that came after. There is also a haunting practical consequence. If the inner core is not just one ball but a layered set of balls, then its rotation, deformation, and dynamics are even more complex than the simple picture used in most models. The slowdown discussed in Chapter 1 may not apply uniformly to every part of it. Different layers may rotate at slightly different rates. The deformation seen at the surface may have nothing to do with what is happening at the very center. Stop and let it sink in. 3,000 miles below your feet sits a solid iron ball the size of the moon. Inside that ball sits another, smaller, even older ball. Inside that older ball, traces of the earliest moments of our planet's life. Each inner doll may be holding clues to a chapter of Earth nobody else can read. These chapters keep reaching back further. Eventually, they reach a moment so violent that it almost ended the planet before life could ever begin. The young Earth was a rough place. Asteroids hit constantly. Volcanoes covered the surface in lava. There were no continents, no oceans, no atmosphere worth breathing. The planet was a glowing, half-molten ball, not yet ready to host life. One key event needed to happen first. The dynamo had to switch on. For a long time, scientists assumed the magnetic field appeared shortly after the planet formed, and hummed steadily ever since. Recent work has changed that picture. Some studies of ancient minerals suggest the field flickered to life early, around 4 billion years ago, but stayed weak. Other studies suggest the field strengthened dramatically only when the inner core began to crystallize, perhaps as recently as 1 billion years ago. If the latter is right, then for most of Earth's history the magnetic shield was a weaker, messier thing than today's. That has consequences. A weaker field lets more solar wind reach the upper atmosphere. Solar wind can strip lighter molecules off into space, including hydrogen and parts of water. Some scientists wonder how much water Earth might have lost during that long period of fragile shielding, and how much survived only because the planet was big enough to recover. The crystallization of the inner core is presented as one of the most important events in Earth's deep history. As iron at the center froze, it released heat. That heat drove stronger convection in the outer core. Stronger convection meant stronger magnetic field generation. The dynamo went from a flickering candle to a steady lamp. Picture a campfire. In its early moments, the flame is uneven, leaping and shrinking. Then a thick log catches fire and burns slowly, providing a steady flow of heat. The fire stops flickering and settles into a constant glow. The crystallizing inner core is the slow-burning log of the geodynamo. Once the field stabilized, life on the surface had a far better chance. Multicellular life, complex life, and eventually intelligent life all evolved under the protection of that strengthened shield. The Cambrian explosion, the rise of fish, the colonization of land, the age of dinosaurs, the rise of mammals, every one of those chapters happened under the umbrella of a strong dynamo. Today, the inner core is still growing. It adds about 1 millimeter of new iron to its surface each year. Multiply that by 1 billion years, and you get hundreds of miles of growth, but the rate is glacial in human terms. We are alive in a moment when the dynamo is strong, but slowly evolving. The same engine that blossomed when the inner core crystallized continues to feed our shield right now. There are concerns. The shield is not constant. As shown in earlier chapters, it weakens in some places and strengthens in others. The South Atlantic anomaly is the loudest current example. A sustained weakening across larger areas would slowly bleed away atmospheric hydrogen and erode the upper atmosphere in ways that take millions of years to matter. Nothing dramatic in our lifetimes, plenty dramatic on the scale of civilizations. The story is not all worry. Life has thrived through field weakenings before. Paleomagnetic records show many such events, and species adapted, migrated, or simply continued. The planet is not as fragile as our nervous systems would have us think. Yet the dynamo's strangest behavior is not gradual weakening. It is full-on flipping, and that has happened many times before. Earth's magnetic poles have flipped their positions hundreds of times during the planet's history. The last full reversal happened about 780,000 years ago. Before that, another and another. Going back, dozens of complete swaps have been recorded in lava flows around the world. Each flow froze the magnetic field of its moment as soon as it cooled, leaving a permanent record of which way north pointed. A flip means that slowly, over thousands of years, the lines pointing north turn around and point south. Compasses, if any existed, would read backward. Auroras, which today dance over the polar regions, would migrate. The shield itself does not vanish entirely during a flip, but it does weaken and become messy, with multiple poles forming temporarily. How long does a flip take? Estimates range from a few centuries to several thousand years. That is fast on geological scales, but very slow on human ones. No human civilization has ever lived through a full reversal. The closest event was the Lachamps excursion about 41,000 years ago, when the field weakened dramatically and partly reversed for several hundred years before snapping back. Some scientists have linked that event to changes in atmospheric chemistry and stress on early human populations, though the connection remains debated. Are we heading toward a reversal now? This is one of the most hotly discussed questions in geophysics. The South Atlantic anomaly's growth has fueled speculation. Yet the lead authors of the recent swarm study made a careful statement. The study did not, however, find any sign of an impending magnetic field reversal. Earth's magnetic field has already reversed hundreds of times. But we know from paleomagnetic records that Earth's magnetic field has weakened many times in the past, displaying weak field regions like the South Atlantic anomaly without reversing. Finley said, "We are more likely seeing a decade to century timescale fluctuation in the field. In plain words, we have seen this kind of weakening before, many times. Without it leading to a flip, the scientists are not predicting an imminent reversal. They are watching a wobble, a worrying wobble, with real costs for satellite operators, but a wobble nonetheless. That said, the long-term odds favor an eventual flip. The average time between reversals is a few 100,000 years, and we are already overdue compared to that average. Some future generation, possibly far in the future, will live through one. They will adapt. They will design satellites with thicker shielding. They will reroute migratory species in protected reserves. They will continue. Picture a giant slow weather system over the entire planet. Most of the time, the wind blows from one direction. Every so often, the system shifts and the wind starts blowing from another. The transition is messy and lasts longer than any human life, but the world survives it each time. The magnetic flip is that kind of weather, just deeper, slower, and built on iron. This long history is also a reminder of how strange the planet truly is. Every other layer is reshaping. The poles are wandering. The shield is splitting. The inner core is twisting. The outer core is jetting. The mantle is sponge-soaked with hidden water. The boundary is patched with ghost continents. None of this matches the simple Earth taught in elementary school. What unifies all these strange behaviors? It may be a single deep secret, a primordial source the planet itself has been hiding from us all along. Step back from the details. Look at Earth as a whole. What you see is essentially a giant battery, slowly discharging over billions of years. Energy is constantly flowing from the deep interior to space, powering plate tectonics, the dynamo, mantle plumes, volcanoes, and even, indirectly, the shape of the atmosphere. The battery's chemistry is more interesting than anyone realized 50 years ago. Iron at the core is interacting with hydrogen, carbon, oxygen, and trace amounts of other light elements. Each of those interactions can store and release energy. The hydrogen stash discussed in earlier chapters may be one of the most important. A core full of bonded hydrogen is a core full of slow-burning chemical potential. There are also nuclear fuels, trace amounts of uranium and thorium dissolved in the mantle, and possibly the core release heat as they decay. These fuels are not like nuclear reactors at the surface. They are diffuse, spread thin, and quiet. But over the size of a planet, even a thin spread adds up. Together, the chemical potential, the radioactive heating, the leftover formation heat, and the latent heat of inner core crystallization make Earth a battery unlike any other in the solar system. Mars is smaller and cooler. Venus is roughly Earth-sized, but seems to have lost its dynamo through a different path. Mercury has a magnetic field, but a far weaker one. The Moon's battery died long ago. Among the rocky worlds we know, Earth is the most active, by a wide margin. That activity is what life feeds on. Without it, the surface would not be recycled, carbon would not be drawn down by subduction, new rock would not rise at mid-ocean ridges, the atmosphere would not be replenished by volcanic gases, climate would not be slowly stabilized over millions of years by the long carbon silicate cycle. Each of these systems depends on a hot, restless interior. Picture a watch with a self-winding spring. As long as the watch keeps moving, the spring keeps tightening, and the gears keep turning. Earth is a self-winding watch driven by its own internal heat and chemistry. The watch will not run forever, but it has been running long enough to allow a sequence of life forms to evolve, each more complex than the last, ending, so far, in us. Yet a watch can have surprises. It can run a little faster for a while, or a little slower. It can develop new ticks. The deep planet has been quietly doing exactly that, surprising scientists. Sending pulses, changing its day length, splitting its shield, reshaping its heart. The battery is far from dying, but its behavior is more nuanced than older models suggested. A practical question follows. If the battery is more dynamic than we knew, can changes inside it ever scale up to changes we can feel? In the short term, mostly no. The deep planet operates on timescales much longer than human ones. In the medium term, yes. The moving magnetic poles already affect aviation. The South Atlantic anomaly already affects satellites. The day-length variations already affect timekeeping systems. In the very long term, yes again. Geological history is full of moments when changes deep in Earth created enormous changes at the surface. Supercontinents rose and broke apart. Climates swung from greenhouse to icehouse. Mass extinctions occurred. The connecting wire ran from deep to shallow. That brings up one of the most haunting possibilities: the connection between deep events and surface disasters. Most volcanic eruptions are local events, fed by shallow magma chambers, sometimes fueled by water from subducting plates. They build mountains, dust the sky with ash, and occasionally bury cities. But every so often in deep history, a different kind of eruption appears, an eruption so large that it reshapes continents and sometimes drives mass extinctions. These are called large igneous provinces, and the leading theory is that they begin near the core mantle boundary. Picture a mantle plume forming above one of the great blobs discussed in Chapter 5. As the plume rises through the mantle over tens of millions of years, its head swells. When it finally reaches the underside of the crust, it spreads out into a giant pancake of hot rock. That rock cracks the crust above and pours out as floods of lava covering vast regions. Some past floods have buried areas the size of Western Europe, under layers of basalt thousands of feet thick. The Siberian traps, formed about 250 million years ago, may be the most catastrophic example. They erupted in a geological eye blink, releasing huge volumes of carbon dioxide and sulfur into the atmosphere. The resulting climate shock is widely considered a key driver of the Permian extinction, the worst mass extinction in Earth history, which wiped out more than 90% of marine species. The Deccan traps in India erupted around the time of the dinosaur extinction, 66 million years ago, and may have weakened global ecosystems even before the asteroid struck. The connection to the deep core is real, even if many details remain debated. As scientists trace the roots of these eruptions through tomographic images of the mantle, they find columns reaching down toward the African or Pacific blob. The rooftop of the core seems to be the launching pad for the most violent volcanic events in our planet's history. Why does this matter for the present? Because the same engine is still running. Today's mantle plumes feed today's hotspots, including Hawaii, Iceland, Yellowstone, Reunion, and others. None of these is currently doing anything close to a Siberian traps eruption. They are dribbles compared to those floods, but the system that produces such floods has not gone anywhere. It is older than animals and shows no signs of stopping. Honest scientists are clear that no one expects a flood basalt eruption tomorrow. These events develop over geological timescales, with decades of warning signs that we would almost certainly detect. The risk in any given human lifetime is essentially zero. The risk over millions of years is significant, but it is a problem for our descendants, not for us. Picture a slow, invisible kettle on a giant stove. The water inside is the mantle. The flame is the core's heat. Most of the time, the kettle simmers gently. Every 100 million years or so, the heat builds in one spot until it sends up a column big enough to knock the kettle's lid loose. When that happens, lava floods rush across continents and the climate twists. This deep thread, from core heat to continent-burying eruptions to mass extinctions, is one of the most striking discoveries of modern Earth science. It connects the inner workings of our planet to the very story of life itself. Every species that ever lived owes some debt, good or bad, to the engine 3,000 miles below. The same engine is also responsible for moving continents, and the way that movement is changing is yet another mystery scientists are still chasing. School children are taught that continents drift, pushed apart by seafloor spreading at mid-ocean ridges and pulled together where plates collide. Africa is moving north toward Europe. The Americas are moving west away from Africa. Australia is racing northeast toward Asia. These are confirmed motions, measured year by GPS stations around the planet. What older textbooks did not show is how variable those motions are. Some plates are speeding up, some are slowing down. The directions can wobble subtly over millions of years. Subduction zones can flip. Continents can change paths. Recent reconstructions of plate motions over the past 200 million years reveal surprising twists. The Indian plate, for example, sped up dramatically before slamming into Asia and building the Himalayas. The Pacific plate has changed direction several times. The Atlantic Ocean has opened in stops and starts. Each acceleration and deceleration must be powered by something. The leading suspects are the deep mantle flows and the heat patterns near the core. When a slab of cold crust dives at a steep angle, it pulls hard on the plate behind it. This is called slab pull, and it is one of the strongest forces driving plate motion. Slab pull depends on how far and how steeply the slab can sink. The configuration of the deep mantle, including the giant blobs and the ULVZs at the core mantle boundary, controls where slabs can go and how easily they can dive. Change the deep configuration and the surface motions shift. There is also the mantle wind. The slow flow of rock from upwelling regions to downwelling regions drags the plates above. Where the deep blobs sit, plumes rise. Where slabs have piled up, the mantle sinks. The plates ride this wind like leaves on a slow river. Picture a giant, almost frozen river, flowing only an inch a year. On its surface float thin sheets, the continents and ocean basins. The river's eddies and currents are set by the heat of the core below. As the heat patterns shift, the eddies shift, and the sheets above must respond. Why does this matter to people on the surface? Because plate motion drives earthquake patterns, mountain growth, and the long-term shape of climate. The opening and closing of ocean gateways changes ocean currents, which changes climate. The closing of an ocean between continents can dry out interiors. The opening of a new sea can transform deserts into coastlines, given enough time. Today's plate motions are still, on average, similar to those of the past few million years. There is no reason to expect dramatic shifts in our lifetimes. Yet the long-term pattern is full of surprises, and the recent realization that the deep mantle is more dynamic than once thought makes us pay more attention to what could change. There is also a humbling thought. Most people have lived their entire lives on the same continent. From a planetary view, those continents are racing across the globe, slowly enough that we never notice, but quickly enough that over millions of years, every shoreline you remember will be unrecognizable. The Atlantic will be wider, the Mediterranean may be gone, Africa may have plowed into Europe. New mountain ranges will rise where flatlands sit today. All of it is steered in the end by what is happening deep below the surface, including a slow process at the very rooftop of the core that may surprise you most of all. Iron snow. Look up at the night sky in winter, and you might imagine snow falling from the clouds. Now invert the picture and aim it deep into the planet. At the rooftop of the outer core, scientists believe a different kind of snow may be falling. Not water ice, not frozen carbon dioxide, iron crystals, freezing out of the molten metal and drifting down toward the inner core. Here is the chemistry. The outer core is a hot swirling alloy of iron, nickel, and lighter elements like sulfur, oxygen, and hydrogen. Near the boundary with the mantle, conditions are slightly different than deeper down. In some regions, scientists suspect that small iron crystals can begin to form right at the top of the outer core. These crystals are denser than the surrounding liquid, so they sink. As they fall, they may melt back into the fluid before reaching the inner core. Or they may make it all the way down and stick to the inner core's surface, helping it grow. This is presented as a strong theory, supported by lab experiments and by some seismic features in the deep core. Direct observation is impossible, but the picture, if correct, is breathtaking. Imagine a slow snowstorm of glowing iron flakes inside a sea of liquid metal. The flakes rise and fall, some dissolve, some pile up. Over millions of years, this snow contributes to building the inner core, layer by layer. The snow may also affect the magnetic field. As iron crystals form, they release the lighter elements that were dissolved with them. Those lighter elements rise. Their rise drives convection. Their convection feeds the dynamo. So the snow, in addition to being a cosmic curiosity, is part of the engine that powers the magnetic shield around the planet. Picture a glass of fizzy soda. Bubbles rise. The drink stays in motion as long as bubbles keep coming. In Earth's outer core, the bubbles are not gas, but light elements left behind by freezing iron. They rise toward the mantle and stir the metal as they go. The shield above is partly the result of this slow planetary fizz. There is also a darker possibility. Some researchers have argued that iron snow is not uniform around the rooftop of the core. Different regions may produce different amounts, depending on temperature and chemistry. Patchy snow could create patchy convection, which could create patchy magnetic field generation. That patchiness could be one ingredient in the strange features of the modern field, including the South Atlantic anomaly and the moving anchors over Canada and Siberia. Stop and try to picture all of this together. A solid iron ball at the center, possibly superionic, with a smaller older ball nested inside it, growing slowly as iron snow falls onto its surface. Around it, a swirling liquid metal sea, threaded with jets and reverse flux patches and broken into uneven snow zones. Above, a layered pockmarked boundary studded with ghosts of ancient seabeds. Above that, 2 continent-sized blobs and a water-soaked mantle. And on top, the thin film of crust where every river runs and every city rises. That is your planet, strange, layered, alive in places we will never visit. The strangest thing of all is what these observations mean for our place in the universe, because Earth, with all this internal drama, may be more unusual than scientists once realized. For a long time, planetary scientists assumed that any rocky world of similar size to Earth would have a similar internal engine: iron core, rocky mantle, magnetic field, plate tectonics, standard package. The galaxy seemed full of potential Earths waiting to be found. Then Mars and Venus broke that assumption. Mars is about half the size of Earth. It cooled faster. Its dynamo died. Its magnetic field is now only a faint whisper, mostly preserved in old rocks. With no shield, the solar wind has stripped away most of its atmosphere. What remained froze or escaped. The river valleys carved when the planet was younger sit dry and dusty. The story of Mars is the story of a planetary battery that died. Venus is roughly Earth's size, but it has no global magnetic field today. Its interior is hot, but its dynamo, if it ever had a strong one, is not functioning now. Its surface is hot enough to melt lead, with a thick, choking atmosphere of carbon dioxide. Plate tectonics, as we know it on Earth, does not seem to operate on Venus. The crust there appears to be a single shell that occasionally resurfaces in catastrophic global events. Why? Why does a planet so similar in size to Earth behave so differently? The honest answer is that we are not sure. Earth, sitting between these two, is an outlier. Its dynamo is strong. Its plate tectonics is steady. Its magnetic shield protects an atmosphere that has supported complex life for hundreds of millions of years. The chain of conditions that makes this possible is long and surprisingly delicate. The planet had to be the right size, with the right composition, with the right amount of water, with a moon big enough to stabilize its tilt, with the giant Jupiter shielding it from too many impacts, and with a hot, active core that did not cool too quickly or too slowly. Picture a chain of dominoes. Each tile must fall just right for the next to work. Tilt it slightly, and the chain breaks. Earth's interior life depends on a long chain of dominoes that all happen to land cleanly. Other rocky worlds in our own solar system show what happens when even one tile falls wrong. Why does this matter for the search for life elsewhere? Because finding rocky planets in habitable zones is only the first step. The next step is asking whether they have living interiors. A planet without a dynamo may have no shield. A planet without plate tectonics may not recycle carbon and stabilize its climate. A planet without a hot core may have no volcanism, no replenishment of atmosphere, no engine to keep it dynamic. That is sobering. It means the universe might be full of planets that look superficially Earth-like, but lack the deep engine that makes Earth livable. A blue dot in a telescope is not enough. We need to know what is happening at its core. The good news is that future missions may begin to detect such things indirectly. The strength of a planet's magnetic field can be inferred from its interactions with stellar wind. The presence of plate tectonics can sometimes be inferred from atmospheric chemistry. Scientists are slowly learning how to listen for living interiors across light years. In the meantime, this realization should change how we look at our own planet. The deep engine is not background, it is what makes us possible. Treat it with awe. There is one more layer to this awe, because the engine, deep as it is not entirely separate from the cosmic events happening above us right now. Earth's magnetic field does not just sit and shine, it interacts. Above the atmosphere, the solar wind, a constant stream of charged particles from the sun, presses against the field. The boundary where the two meet is called the magnetopause. On the day side of Earth, the magnetopause sits about 10 Earth radii above the surface. On the night side, the field stretches into a long tail extending past the orbit of the Moon. When the sun is calm, the magnetopause stays comfortably far. When the sun erupts, in events called coronal mass ejections, billions of tons of charged plasma are flung at the planet. The magnetopause is shoved inward. Sometimes it is squeezed close enough that satellites in geosynchronous orbit briefly find themselves outside the protective bubble, exposed to raw solar wind. The deep core engine, which generates the field, also sets the limits of how far solar storms can intrude. A stronger field deflects more particles. A weaker field, including the South Atlantic anomaly, lets more particles dip closer to the surface. We saw glimpses of this connection already. Now imagine it scaled up. The most powerful solar storm ever recorded by instruments was the Carrington event of 1859. Telegraph lines sparked. Auroras were visible at very low latitudes. If a Carrington-class event hit modern infrastructure, the consequences would be far larger. Power grids could be damaged. Long pipelines could absorb induced currents. Satellite electronics could fry. Trillions of dollars of damage are easily imagined in worst-case scenarios. How likely is such an event? Estimates vary, but most agree the chance in any given decade is non-trivial. Geophysicists are taking the risk seriously. Modern grids are being studied for vulnerability. Spacecraft are being designed with stronger shielding. The South Atlantic anomaly is being monitored more carefully than ever, partly because a major solar storm during a moment of weakened shield would amplify damage. This is where the deep planet meets daily life in a tangible way. The currents in the outer core, the snow at its rooftop, the thinning patch over the South Atlantic, all combine to set how much margin the planet has when the sun acts up. Most days that margin is comfortable. On rare days it might not be. There is a hopeful side. The same Earth that protects us so well does so because of its restless interior. Without the molten outer core, no field. Without the field, no shield against the sun. Without the shield, no rich atmosphere. Without the atmosphere, no surface life. The chain runs all the way from solar storms to inner core dynamics, and back. Picture two hands. One hand is the sun, slowly flexing its fingers, occasionally clenching into a fist and punching outward. The other hand is the deep core, holding up a curved shield in front of the planet. Most punches glance off. Occasionally, one slips through the cracks in the shield, and a city's power grid flickers. The story between these two hands has gone on for billions of years, mostly invisible to us until very recently. We are now starting to watch both hands at once, with satellites monitoring the Sun and Earth's field together. That gives us a chance to predict, prepare, and reduce damage. The future of civilization in space partly depends on how well we read this dance. It also depends on a deeper question. What lies at the very edge of our knowledge of the deep planet, in places where even the best instruments cannot quite reach? For all the breakthroughs of the past few decades, vast stretches of Earth's interior remain dark. Instruments have improved dramatically, but they still cannot see everything. Seismic networks are dense in some regions, sparse in others. Most of the southern hemisphere is harder to study than the northern one, simply because there are fewer instruments. Large areas of the deep mantle and core are still mapped only at coarse resolution. The deepest direct sample of Earth's interior comes from the Kola superdeep borehole in Russia, drilled through the crust to about 7.5 miles down. That is barely a scratch. The crust beneath the oceans is roughly 5 miles thick. The continental crust averages around 25 miles. The mantle goes down nearly 1,800 miles. The core extends another 1,400 miles below that. Our deepest physical reach has touched only the upper part of the crust. Everything we know about the deeper layers comes indirectly. Seismic waves bounce off boundaries and reveal them. Magnetic measurements at the surface and in space reveal the dynamo's behavior. Gravity maps show density variations. Lab experiments squeeze tiny samples to core-like pressures and observe how they behave. Each method has limits. Each one tells us part of the story. Some of the deepest mysteries are still wide open. We do not fully know what causes the ULVZ structures at the core mantle boundary, or whether they are uniform in composition, or how they evolve. We do not fully know why the inner core is layered, or how fast its layers rotate relative to one another. We do not fully know how much hydrogen is locked in the core, or how that hydrogen might be released. We do not fully know why the recent slowdown happened, or whether it will continue, or whether it foreshadows other changes. There are also human limits. The scientific community studying the deep interior is small. Compared to the budgets devoted to space telescopes, mantle and core research is a quiet field. New seismic stations cost money. New satellite missions cost more. Lab work on diamond anvils requires rare equipment and skilled hands. Progress is steady but constrained. And yet, the speed of recent progress is striking. 20 years ago, we did not have swarm. 40 years ago, we did not have grace. 60 years ago, we did not have plate tectonics. A century ago, we barely knew the inner core existed. Each generation has been able to peer deeper than the last, and there is no reason to expect that trend to stop. Picture a slowly opening window. For most of human history, the window onto the deep planet was painted shut. In recent decades, it has cracked open, and a beam of light is reaching into rooms no one had ever seen. Each new instrument opens it a little more. Each new theory makes the rooms inside clearer. There are still many rooms beyond what we can see, but we are no longer staring at a blank wall. This is part of why the recent discoveries feel exhilarating, even when they are unsettling. The slowdown of the inner core, the splitting of the South Atlantic anomaly, the ghost continents at the core boundary, the snow of iron near the rooftop of the molten ocean, none of these would have been known a generation ago. Many were not even predicted. The deep planet is finally being heard. And with that hearing comes responsibility, including the duty to act on what we learn. After all this strangeness, a simple question: should any of it change how you live? In day-to-day terms, mostly no. The deep planet operates on timescales far slower than human ones. You will not feel the inner core reverse. You will not notice when iron snow falls. You will not see the South Atlantic anomaly with your own eyes. The coffee you drink tomorrow morning will taste exactly like it did yesterday. In broader terms, however, the picture matters more than people realize. 3 concrete examples follow. First, navigation and aviation. The wandering magnetic pole and the changing field already affect compasses, runway designations, and pipeline surveys. Airports have had to renumber runways as the magnetic north shifted. The world magnetic model is updated more often than before. Global shipping, military operations, and commercial aviation all depend on this work. If you have ever flown internationally, the precision of your flight depended in part on people quietly tracking the deep core. Second, satellites and infrastructure. Companies launching constellations of low-orbit satellites must account for the South Atlantic anomaly and for solar storms enhanced by deep field weakening. Power grids in high-latitude countries take precautions to avoid catastrophic damage from geomagnetically induced currents. Communications, weather forecasting, and even financial systems rely on continuous operation of these vulnerable assets. The deep planet quietly shapes the reliability of services people use every hour. Third, long-term stewardship. Earth's deep engine is what makes the surface livable. Plate tectonics buries carbon and sustains the long-term climate cycle. The dynamo shields the atmosphere from being stripped away. Volcanoes replenish gases and minerals. None of these processes can be controlled by humans, but they can be respected. Decisions about climate, biosphere protection, and long-term planning are healthier when made with awareness of how thin and dependent the surface really is. Picture a tiny garden planted on top of a giant sleeping dragon. The garden has thrived for thousands of years because the dragon has dreamed gentle dreams. The garden's caretakers have never seen the dragon, but they know it is there. They know it warms the soil. They know its breath shapes the weather. Most of the time they live their lives without thinking about it. But when the dragon stirs, even slightly, the gardeners pay attention. They tighten the fences. They check the wells. They stay humble. That is roughly the right relationship with Earth's interior. Awe, yes. Curiosity, yes. Casual disregard, no. We are thin film life on a hot, restless world. There is also a deeper personal point. Knowing what is below you can change how you stand on the ground. The next time you walk on a beach, in a forest, or on a city sidewalk, try imagining the layers beneath your feet, the crust, the water-soaked mantle, the blobs, the boundary with its ghost seabeds, the swirling outer core with its hidden jet, the solid inner core slowly turning the wrong way. The innermost ball, possibly older than animals, possibly superionic, holding tens of oceans of hydrogen. Every step you take is a step on top of all of that. Every breath you take is shielded by it. Every compass needle that points north is pointing because of it. After all this, only one big question remains. What might still be hiding down there, beyond what current science can detect? If the past few decades have taught geophysics anything, it is humility. Each time scientists thought the deep Earth was nearly figured out, a new instrument revealed a new layer of strangeness. The inner core was supposed to be a simple solid ball. Then it was found to rotate. Then it was found to slow. Then it was found to reverse. Then it was found to deform. Then it was found to be possibly superionic. Then it was found to be layered. Each step felt like the final answer until the next step came. What might still be hiding? Several open questions stand out. First, how unique is the inner core's behavior? We have only watched it carefully for a few decades. What if the patterns we see are part of a longer cycle that includes events far stranger than slowdowns? Some researchers have raised the possibility of past episodes when the inner core's rotation was much more chaotic. We do not yet have the data to confirm or rule that out. Second, what really happens at the core mantle boundary on small scales? The maps we have today resolve features hundreds of miles wide. Smaller features, 10 or 20 miles across, are still essentially invisible. Yet much of the chemistry and dynamics of the boundary may live at those smaller scales. The next generation of seismic networks may reveal entirely new structures we cannot yet imagine. Third, how do all the layers truly connect? We know the inner core, outer core, and mantle interact. We know gravity, magnetism, and seismology each provide a partial view. We do not yet have a single unified time-resolved picture of how these layers move together. Building such a picture is one of the big projects of modern Earth science. It will take decades of more data and bigger computers. Fourth, what is the long-term fate of the dynamo? The shield has already weakened in places. The poles are wandering, the day length is wobbling, the inner core is changing. Are we in a normal multi-decade fluctuation, or are we at the edge of a longer transition? Honest scientists will say we do not yet know. The data points in many directions, and the timescales involved are longer than our records. Fifth, the most haunting question of all, are there structures in the deep planet that we have never even suspected? The discovery of the innermost inner core, the mantle blobs, the ULVZ structures, and the recycled seabeds was unimaginable a few generations ago. There is no good reason to assume the discoveries are over. Future seismic networks, better gravity satellites, and improved lab work will almost certainly reveal features we cannot guess at right now. Picture a vast, dark cave that humans have only just started to explore with weak flashlights. We have mapped a few rooms, we have heard echoes from many more. We know that some sections lead deeper than the flashlights reach. The cave is the planet's interior. The flashlights are our instruments. We are early in the exploration, far earlier than the confidence of older textbooks suggested. The good news is that the next generation of geophysicists will probably solve mysteries we cannot even formulate clearly today. The Earth has been waiting 4.5 billion years. It is in no rush. We can keep listening. After all this, the journey downward must end somewhere, not at a boundary, but at a perspective, a view of our planet that pulls all the chapters together. Step all the way back. Imagine Earth as seen from far away, a blue and white marble hanging in black space. Most of what makes that marble alive is hidden inside it. The crust we live on is a thin skin. The mantle below is a slow-flowing stone river. The outer core is a sea of glowing iron. The inner core is a solid ball with secrets older than animals. Around all of this is a magnetic shield, born from deep flows, that fends off the sun's wrath and keeps the air breathable. Every chapter of this video has shown one truth from a different angle. Earth is not a dead rock with weather on top. Earth is a vast, layered engine, restless from center to surface, alive in the deepest possible sense. Plate tectonics, volcanoes, earthquakes, magnetic shields, climate cycles, and the long history of life are all branches of the same tree, with roots reaching down to the iron heart. Recent science has changed our understanding of that engine in profound ways. The inner core is slowing and reshaping. The magnetic shield is splitting in places and growing in others. The planet's day length is wobbling. The deep mantle holds hidden continents and oceans of water. The core itself may hold tens of oceans worth of hydrogen, and may be a state of matter physics is only now naming. None of these were known to your great-grandparents. Most were not known to your parents. What does this mean for our place in the universe? It means that habitable planets are not just about distance from a star, or the presence of liquid water. They are about engines. They are about cores. They are about whether a world can hold its heat long enough to keep its magnetic shield, its atmosphere, its plate tectonics, and its long carbon cycle alive. Earth has done it. Mars and Venus have not, for different reasons. The lottery of habitability runs not only on the surface, but on the deep interior. What does it mean for daily life? less than you might think. The world will keep turning, coffee will keep being made, children will keep being born. None of the deep changes is fast enough to disrupt any of that. Yet there is a quiet shift in mood that comes from knowing the planet beneath you is alive. Walking on the ground feels different when you understand what it is sitting on. Picture standing on a beach at sunset. The sand under your feet is part of the crust. Below it, hundreds of miles down, the mantle is slowly flowing. Below that, a sea of iron is generating the magnetic field that protects the sky above your head. Below that, an iron ball the size of the moon is twisting slowly, deforming, glowing with the heat of formation. The sun setting in front of you is hurling charged particles toward the planet at this very moment. Most of them are bouncing off the shield made by the metal heart below. Without the shield, no air, no oceans, no you. That is what Earth really is, a miracle of layered conditions, wrapped around a hot, restless engine, holding a film of liquid water and life on its outermost skim. We are tiny passengers riding the shield of a giant, ancient machine. If this journey gave you a new sense of awe for the world below your feet, share it with someone. Send it to a friend, talk about it at dinner, look up at the night sky knowing that the most wondrous structures in the universe might be standing right under you. And keep watching. The deep planet has not finished sending its signals. The next discoveries may be only months away. Earth is alive, and it is just getting started teaching us how.